Let's draw a circle of radius 1. We'll pick a point on the circumference of the circle and we'll draw the radius. We define something called an angle in degrees by splitting the circle into 360 equal segments. Now we define the angle sitting with the horizontal as 0 degrees, and you can see this here in the drawing. Now we're going to rotate this angle around about the circle in an anti-clockwise direction, and we're going to map out all of the 360 degrees, and you can see this angle being mapped out now, and we've got an angle of 90, and then it travels round to 180, and then to 270 degrees, and finally it goes all the way round to 360 degrees, which is equivalent to 0 degrees. Let's take this back to 0 degrees, and we'll zoom in to take a closer look. So you can see that the arc length of 1 degree is given by this distance, and then 2 degrees is this distance here, and then 3, 4 and 5 degrees. So an arc length here of this distance is given by an angle of 5 degrees. So why split the circle into 360 segments? Why not split it into 10 or 100 or 1000? Is there anything in particular about 360 that makes this choice a better choice than any others? Well, the only reason is historical, and this is because the number 360 is easily divisible by lots of other numbers. For example, 2, 3, 4, 6, 12 and so on. This made arithmetic calculations a lot simpler in times when we didn't have access to calculators. So the choice of 360 is purely historical. Now the next question is there a better way of measuring angles rather than using degrees? And the answer is yes. We're going to look at measuring in radians. And we're going to look and see 3 examples of why measuring in radians is a much more efficient way of measuring angle than measuring in degrees. Let's say we're given the angle 5 degrees and we want to find the arc length. So that's the distance between this point here and this point here. So we want to find an equation which will generate this arc length. If we were to measure the circumference of a circle and divide it by the diameter of the circle, then we would get a fixed number, and this number would be approximately 3.14159. So this is the circumference divided by the diameter, and this is the same for any circle. So for example, if we measured the circumference of the moon and divided it by its diameter, we would get this number. If we took the circumference of a snooker ball and divided it by the diameter, we would get this number. Now we give this number a special name and we call this number pi, and it's written like this. So we can rewrite this equation as pi is equal to the circumference divided by the diameter. Now we could write this out in terms of the radius, because we know there's going to be 2 values of the radius for each of the diameters. So we could replace this d here with 2 times r. So we have the equation pi is equal to c upon 2r. We can rearrange this to give us the circumference. So the circumference of our circle is equal to 2 pi r. So we know how to work out the circumference, but in this example here, we're not going all the way round the circumference, we're only going round 5 degrees. That is, we're going 5 360ths of the way round. So it means that if we were to take 5 divided by 360, that will give you the ratio of the distance round the circle. And if we multiply this by the circumference, which is 2 pi r, we're going to get the little arc length. So we're going to have 5 upon 360 times 2 pi r will give us the arc length, which we'll call L. Now we can divide out the 2 and the 360, and this will give us 5 upon 180. So we've got a general equation which we can use, and we can write that the arc length L is going to be pi divided by the 180 times the radius times the angle here, which in this instance is 5, but in general we'll just call an angle of theta in degrees. In order to work out the arc length at an angle of 5 degrees, we take the value of pi, we divide this by 180, we then multiply it by the radius. So let's say in this instance the radius is just a value of 1. And then we multiply it by the angle. In this instance the angle is 5 degrees. So this will give us an arc length of 0.087266. So this is the value for the arc length in this instance, 0.087266. Now we can also rewrite this equation here, and instead of working out the arc length given the radius and the angle theta, we can work out the angle theta given the arc length L and the radius. So we've just rearranged this equation here and made theta the subject. So you can see that we've got these neat little equations that relate angle to length or length to angle. And you can see that they're actually quite simple equations. If we were to read them out, we would have L is equal to r theta and theta is equal to L upon r. But there is a problem here, is that we've always got this scaling factor whenever we go through this conversion, and the scaling factor is pi upon 180 or 180 upon pi. Now the scaling factor occurs because we're measuring our angles in degrees. So is there a way of getting rid of this scaling factor so that we're only left with the simple equation L is equal to r theta and theta is equal to L upon r? So that is that there's a direct relationship between the angle theta and the length L, or equivalently the length L and the angle theta. And we don't need to go through this scaling factor of pi upon 180. Well, there is, so let's have a look and see how we're going to do that. Mathematically, all we want to do is get rid of this pi divided by 180. So in order to do that, you would multiply this here by 180 upon pi. So this 180 would cancel with this one, the pi would cancel with the pi, and you would just be left with the value of r theta. So whenever you scale it up by this 180 by pi, you're not scaling up the radius is a fixed value. But what we're doing is we're scaling up the angle. So in this instance here, we're going to scale by 180 upon pi. So let's see what this value is on the calculator. So we're going to have 180 divided by pi. And you can see this is an angle of 57.29577 degrees. So let's put this angle into the simulator and we'll see what it gives us. So let's rotate this angle round to the 57.295 29577, and we'll watch and see what happens to the arc length. So as this rotates round, the arc length here is increasing, and you can see as it tends towards 57 degrees, this arc length is tending towards a value of 1. So what we have done is we've scaled the angle in degrees up by a factor of 180 upon pi, which gets rid of this pi upon 180, which just gives us the equation L is equal to r theta. So now we have a direct relationship between the angle theta and the arc length L, such that L is just equal to r theta. So we have our new equations, L is equal to r theta and theta is equal to L upon r. But the thing to know about this is that the angle theta here is not in degrees. The angle theta is in our new scale. And our new scale we're going to call radians. And if we were to convert, we could see that the angle 57.29577 degrees would be equivalent to 1 radian. So this would be 1 radian here. So we get 1 radian whenever we have an arc which is equal in length with the radius. So for example, the radius here is a value of 1 and the arc length is a value of 1. In that instance then, the angle here is 1 radian, which is what you would expect because you would have 1 is equal to 1 times 1. So how many radians are we going to have in a full circle? Well, we could take the 360 degrees of the circle and divide it by our 57.29577. Equivalently, we could look and we could say, if this circle has got a radius of 1, then we know the circumference is going to be 6.28. So that is just 2 times pi times r. So it's 2 times pi times 1. 2 times pi is 2 times 3.14, which is 6.28 approximately. So we're going to have 6.28 radians in the full circle, or equivalently we can say we're going to have 2 pi radians in a full circle. So 2 pi radians is equal to 360 degrees. So let's summarise what we've learned in this video about radians. We said that we have a new scale for the angle, and we said that the new scale is 1 radian is equal to the angle subtended by an arc, which is equal in length to the radius. So the arc here is equal in length to the radius, and it's going to generate 1 radian. We also said that 2 pi radians is equal to 360 degrees, or equivalently pi radians is equal to 180 degrees. So this is the one we want to remember here. Pi radians is equal to 180 degrees. Now we also want to know how to convert from degrees to radians and also radians to degrees. Now we can see how to do that from the equations here. Now remember from the previous page that these equations related the angle theta in degrees to the arc length, or equivalently the arc length to the angle theta in degrees. And we noted we're always going to have this scaling factor of either pi upon 180 or 180 upon pi. Now if we wanted to go from degrees to radians, then we can say down here that in this instance here we have theta in degrees here. If we wanted this to be theta in radians, so if we put theta again, now if it's not got the little degree sign, we assume that means radians. So in order to get that here into theta in radians, we've got to get rid of this 180 upon pi. So we get rid of that by multiplying this by pi upon 180. So we're going to have our 180 upon our pi, and we're going to have our L upon our R. So in order to get it into radians, we've got to get rid of this. So we get rid of this by multiplying by pi and dividing by 180. So in that case then, these would cancel out, these would cancel out, and we'd just be left with theta is equal to L upon R. So that's what I've done up here. We've taken the degrees here and we've multiplied it by pi divided by 180. So to go from degrees to radians, you multiply by pi upon 180. Now to go the other way around about, if you want to go from radians to degrees, then we're going to have to add in the factor of 180 upon pi. So we're going to have to multiply radians by 180 divided by pi. So let's go ahead and we'll look at some of this in the simulator, and on the next video we'll just go through a few examples to ensure you understand how this is working. This simulation file is available to you in the resources section, so you can go ahead and open it up and have a little play with it. Now what we have here is a circle, and the circle is actually broken into individual degree elements. So we're going to have 360 degrees all the way around this circle. So from this point to that point is 1 degree, and then it's 2 degrees, 3 degrees, and all the way around the circle until we get to this point here, which will be 359 degrees, and then up to 360 degrees. Now what we're going to do is we're going to rotate a phaser round about this circle, and we're going to compare the value of our degrees to our radians. So I'll press play on this just now and we can watch this work its way round. So there's a little pink line here, and you can see it's counting its way round, and that's, you can see the degrees and the radian values. Now if I get up to this blue line here and I'll press pause, we'll see that at this blue line here we're going to have 1 radian. So that is going to sit right over the top of that blue line whenever we've got a value of 1 radian. So 1 radian then is equivalent to 57.29578 degrees, or approximately it's equivalent to 57.3 degrees. So that's another thing to note. 1 radian is equal to 57.3 degrees. Now it's going to travel round to the next blue line, which will be a value of 2 radians, and then it will be 3 radians, 4 radians, 5 radians, 6 radians, and then the bit that's left over is a 0.28, so that's 6.28 radians. So it's going to be 2 pi radians, which is 6.28 radians, is going to equal our 360 degrees. So I'll press play on this, and you can see that it's just going to continue working round about until eventually the radian value is going to go up to 6.28, which is 2 pi, and the degrees value will go up to 360 degrees. Now I suggest that you open this up and have a little play with it and ensure that you understand the scales for radian and the scales for degrees. So I'll let that just run out to the end, and you can see it's gone up to 6.28 degrees, and it actually just goes back and it works its way back again. So we'll go up to the end there, and you can see that 6.28 degrees is actually equivalent to 360 degrees. So why use radians? Well, we've got 3 reasons here in this video. One is it gives us a better scale in order to represent the basic trigonometric functions graphically. Secondly, it directly relates angle and length without any problem with scaling factors, for example 180 upon pi or pi upon 180. Now finally, in mathematics, in particular if we look at calculus, it works under the assumption that you're actually using radians. If you weren't using radians and you were using degrees, then you would have the factor of 180 upon pi or pi upon 180 within all of your calculations. So it's much easier, much simpler and much more elegant to always work in radians. So that's all for this video. I think we've covered radians in quite a lot of detail. In the next video we'll go on and we'll look at a few examples. So thank you for listening. I'll get you on the next video. Goodbye.